Okay, good night everyone. So today we are going to talk about some kind of equation in mechanics and fluids. So we will begin by introducing ourselves. My name is Hercules Padipa from Mechanical Engineering.
My name is Lancesno Pratamalingga from Mechanical Engineering too.
Hello, my name is Muhammad Danendra Zydean Mardika. I'm from Mechanical Engineering.
Okay, so first one is we have to always remember about our steps, which is the day 5 that consists of conscious thinking, intention, initial thinking, idealization, and also instruction. So before we start, we have to say our prayers. There is doa untuk memohon kemudahan, and the challenge is about fluid mechanics equation. So the general intention is about we solve this problem to learn about mechanical fluids for the sake of God, as He is the creator who made us and facilitates us to live in this planet. Maybe Elang can do this problem or Zide.
Maybe I'll let it Danendra to explain the problems first for the first case.
Okay. So we have the first case, and today we will discuss about three cases, and every one of us will explain one question at a time. Okay, so it's me first. The first case is about Bernoulli equation. So the question here is calculate the speed at which liquid flows out a small hole in the bottom of large tank containing liquid to a depth of 1 meters. Also find the volume rate that is derivative volume divided by derivative time for a hole of radius 3 millimeters. So here you see sort of a tank that is in the shape of a tube, and here you can apply the Bernoulli equation. As you know, Bernoulli equations is the velocity. If the velocity is bigger, um, the pressure is smaller, and if the velocity is smaller, the pressure will be bigger. So here we have a few something. The variables that we know is the height is 1 meters. The outlet diameters is 3 millimeters. And also here we know that the pressure is the same, so just the outlet is different. So I think from here we will know about the velocity, right? The flow rate. And the other one is, yeah, so the other one, because the outlet is only 3 millimeters instead of the inlet is bigger, so the reference area is much bigger on the inlet than on the outlet. Okay, so next. Okay, now we've come to the idealization. So we have the Bernoulli equations here is rho 1 plus rho times gravitation times height 1 plus half times rho times velocity 1 quadrat equal to rho 2 plus rho gravity times height 2 plus half times rho times velocity second quadrant. So here in this concept we can use Torricelli's equation. Fun fact about Torricelli's equation is I think they taught us since we were like in middle school, right? So this is like one of that formula that will be usable on other equations, not only Bernoulli equations, I think. And also we have the reference area, you know, A equal to P times R quadrat, which is the reference area for the tube, the because it's shaped circle. You can go next. Okay, so this is the first step because from what we know that the pressure is the same, pressure 1 is the same to pressure 2, so we can just eliminate that, and then from height 1 is 0, so we can put the height into the equation, so it equals 0. So all we have is um, can I annotate this? So Daryl, can you half times rho times velocity 1 quadrat equals 0 also. So the equation for the inlet is equal to 0. And then the pressure 2, you can eliminate that too because it's the same pressure as pressure 1. And then all we have plus the equation is only rho times gravity times height 2 plus half times rho times velocity 2 quadrat. So from that, we can go to this second step, which, as you know, I already called before. The equation become this: 0 equal to rho gh and half rho times the root of 2. Because from the equation, can you go back? Yeah, from Torricelli's equation, we can know that it is the root of 2. Can you go back? Okay. So from there, we can move the rho gh to the side, and then we can count it and eliminate, and then we get the velocity of 4.4 meter per second. Now we can find the balloon flow rate by finding the speed using A equal P times the R quadrat, and then A is the same to derivative P divided by derivative T equal A2 using Torricelli's equation again, and then from that we can found that the volume flow rate is 1.2 times 10 pangkat minus 4 meter cubic divided per second. I think that's all from me. Now we will go into case 2, which is an incompressible flow case, which will be solved by my friend Dara.
I think
Okay.
this one is for Elang.
Yes. Sorry. Okay. So, what I'm going to talk about is and discuss to you, Mr. Dai, and all of my friends that are watching this video is we're going to talk about incompressible flow. And the initial thinking of the problem is we need to learn and study the problem first. So this is the problem, which is water flows through a horizontal branched pipe at the rate of 0.4 meter 3 times square per second. So we have to determine the velocity of the water at point 2, the pressure at 3, and the flow rate at 4. The information that we have is we have the first pipe is D1, or diameter 1 is equals to 0.35 meter. For the flow rate is 0.4 meter square 3 per second, and the pressure is 71 kilopascal. For the second pipe, we have the surface area, which is 6.5 times 10 square 3 minus 3 meter quadrat, and for the pressure is 0.37 bar. And for the third pipe, we have diameter equals to 15 centimeters and the velocity, which is 6 meter per second. For the fourth pipe, we didn't know anything, so we will try to find it. Next one. So, as you know, that idealization is about we have to model, we have to find some formulas to solve the problems. So, incompressible flow are defined as those in which the density of the fluid remains constant. Shear forces on the incompressible fluid due to viscosity or external body forces do not cause changes in density during flow. So, the rho is constant. Next one, please. So the first one is to use Bernoulli for pipe 1 to decide the velocity, not the volumetric flow rate. So we use flow rate divided by surface area, which is 0.4 divided by P times 0.35 square divided by 4 and equals to 4.16 meter per second. For Bernoulli usage, we will use between pipe 1 and 3. So rho 1 plus rho velocity quadrat per 2 plus rho GH equals to rho 3 plus rho V3 quadrat per 2 plus rho GH3. So this is the calculation, 71 times 10 square 3 plus 1000 times 4.16 quadrat per 2 equals to pressure 3 plus 1000 times 6 square per 2. And the pressure is 61.9 times 10 square 3 Newton per meter quadrat. Next one. Okay, so we are going to use Bernoulli equation for pipe 1 and 2 to decide velocity at point 2. So yeah, we use the same formulas, and for some reason the bar, which is 0.37 bar, is used here times 10 square 5 to have the same as the Pascal one, and the velocity at point 2 is equal to 9.24 meter per second. For the next one is we use to calculate the surface area for area 3, which is P times 0.15 quadrat divided by 4, which is 0.0177 meter quadrat, and the A1 is P times 0.35 quadrat divided by 4, which is equal to 0.0962 meter quadrat. We are going to use this for defining the volumetric flow rate in 4. Next one. Okay, so the incompressible flow is flow rate 1. So inlet means equal to the outlet. So 1 or flow rate 1 equals to flow rate 2 plus flow rate 3 plus flow rate 4. And we just use the A, or surface area, times velocity for each component. And we got the flow rate is 0.234 meter cubic per second. Next one.
Okay, so I
Now
think
is compressible flow, and will be explained by my partner Dara.
okay, so now we are moving on to the compressible flow, and as we know, the intention is that we are solving mechanical fluids equation to learn about it. And for the next one, the problem is about when considering flow in a circular pipe, RED critical at around 2300. For flow through a 5 cm diameter pipe, at what velocity will transition occur at 20 degrees Celsius for airflow flow? So we are talking about air. So the first thing that we should do is we are talking about the initial thinking, and we have to find about the properties of viscosity and also the density at 1 atm for 20 degrees Celsius of air. As we can see, the kinematic viscosity is 1.50 E the power of minus 5, and the density is 1.20, and the dynamic viscosity is 1.80 E to the power of minus 5. So the next one is we can move to the idealization. Knowing about all the parameters that we get, we can use the Reynolds number formula, which is velocity times rho times d per the dynamic viscosity. But we can also know that the kinetic viscosity is the same as dynamic viscosity per rho. So we have V equals to 2300 times dynamic viscosity per d. Now after that we can just calculate it in the idealization part, and now we get the velocity of air is 0.69 meters per second. So in conclusion, we can draw a line that anything below 0.69 meter per second is a laminar flow, and anything above it will become a turbulent flow.
Okay, so after we've done discussing about questions occur mechanical fluids. There, I want to review that we have discussed about three questions. The first one is Bernoulli equations. The second one is incompressible flow, and then the third one is compressible flow. I think it's already clear, right? What do you think, guys?
Well, I think I'm agree with you, Danendra, that we learn about all of the stuff in Mr. Dai class, and but I think the most important part is we learn about a new framework called Dai 5, and it made us realize how to think consciously.
Yes, obviously when you compare the E5 to DMAEC, the E5 is the more complete version of DMAEC, which is one of the most ordinary framework in the world. But the E5 provides different, which is more completed and more complex, but it completes all the aspects in life and also in academics. Obviously, when it comes to Mr. Dai's method, analyze and um, I think it was idealization and instruction is very very clear because instruction is about executing the problem solution but idealization is about you modeling the problems first. So I think the A5 is one of the method that you can use in your life, in the daily life, or in academic life. So thank you, Mr. Dai, for providing us a new method and new concept of learning. So I think that's it from me.
Yes, I, I very much agree with Lang, but I want to add something. Why the E5 is a much more complete version of the mic, because the mic have uh, the E5 is also parallel with the mic. The initial thinking parts covers the define and measure part in the mic, and also the idealization part covers the analyze part in the mic, and the last one is uh, control and I in the mic is parallel to instructions in the I, but they have the advantage on in, intentions. Like intentions, I think you will agree with me here, guys. But intention, I think, is one of the most, it's unique, but it's very useful, because it helps us realize that we cannot do such thing or solve many problems without the help of God, and it helps us reminded that we are the creature of God's, that God give us the power to think, to hear, to be conscious. So I think intentions is like the best part of day 5 to me.
Yeah.
And thank you, Padai, for uh, like introduce us to the day 5 concept and conscious thinking. Uh, I think that's all from me. What do you think, guys? Do you guys have anything more to say? I think about, like overall mechanical fluids study in Pak Dai's class. Like, what do you think, guys?
Well, I think by using the DAI5 for framing to answering mechanical fluids or just learning about it, it's make us easier to know about it because we are not becoming some kind of blind user that just use the formula itself, but we are starting to learn about how the formula could come to life, maybe how they're invented and stuff. So we are more curious in the mechanical fluid itself. I think by becoming mechanical fluids, I mean by becoming curious we could survive in the era of AI and any robots because they can replace our job if we are not becoming conscious. So if we are not conscious, what is the difference between us and them? Yeah, do you guys agree about that?
Yes, yes,
Yeah, I
I
completely
really
agree,
agree.
Mike.
Um, do you guys have anything more to add? I think I have. one or two things, but usually when in class, the thing that makes it most interesting is that Pak Dai always have like a real life situation to the uh, chapter we study. Usually, I think I remember when we're talking about like when Pak Dai tried to solve a venturi pipe. I think if you guys remember that he tried to um, find a way how to make a good valve so like the heat can come out of the pipe. And I think it's like one of the most interesting things about Padai classes.
Hey, how about you, Lang? Maybe you can share your learning experience to us.
Maybe you can share your thoughts.
Um, I think I have had enough because uh from you guys' opinions, it's already completed, so I don't want to add more messages. I think that's enough.
Okay.
Any other addition, maybe?
How about Easy Day? Is that it?
Yeah, I
Okay.
think I already said it all.
Okay, so I think that's also all from me, and I would like to say thank you for Padai for always teaching us this whole semester or this half semester. Because of you, we are able to learn about conscious thinking, and it also really help us in the learning process in our life or in our studies. And I would like to end this session. Thank you, everyone, and good night. Wassalamualaikum warahmatullahi wabarakatuh.